Let's move to the other case. What we have here is we have component one diffusing along a long bar, but here we have isothermally, which means that 等温. And the question will be, do we have heat flux passing through this long bar under isothermal conditions? What's your opinion? Do we have a heat flux? So here, first thing come out from your mind probably will be how many driving force acting on these materials. So probably two, right? The first one is component one, the chemical potential gradient of potential component one, and the second possible driving force probably will be the temperature gradient. Even though we don't have it is isothermal conditions, which also which demonstrate that the temperature gradient equals to zero, but you still have yes now you don't have temperature gradient, but you still have one driving force, which is chemical potential gradient. So is negative chemical potential gradient. So for atomic flux can be expressed as negative chemical potential gradient times the L11. But for the question we just asking, this atomic flux is reasonable, right? Because based on the questions, we do have component one diffusing along these materials. But how about the heat flux? Even though we don't have a temperature gradient, but the heat flux also be driven by the negative chemical potential gradient. Okay, so the coupling term actually is L capital Q1. So based on the atomic flux and heat flow, you can link the heat flux in terms of atomic flux. And here, before we talking about this, so I try to use this heat flux to interpret where this heat flux come from. So even though we have this coupling term, which means that L capital Q1 divided by L11, and this actually link with the heat transport, so can be written as T as 1 bar partial atomic entropy plus the heat of transport. So based on the first term, we know the heat flux actually coming from where? The first one is the heat flux caused by the flux of entropy. Because J1 is the numbers of atom passing through this area per unit time, and U times is contribution on mixed entropy. So actually you can consider as flux of entropy. Okay, and you also times the T, so you got the unit for is in joules. And the second term is you also have the atomic flux, right? But the term is heat of transport. So this term actually is coming from the coupling term between the atomic flux and heat flow. Okay, so some people also will be take the atomic flux outside, so we got less results. Just a simple mathematics technique. But here, I just want to remind you by using this example, demonstrate that even the conditions you have is isothermal conditions. And when there's atomic flux, and which demonstrate that the diffusion happens, and for sure there will be a heat flux passing through these materials due to even though we don't have the temperature gradient, but other driving force will contribute the heat flux. And in this case, chemical potential gradient, negative chemical potential gradient, which directly driven the atomic flux or atomic flow, will contribute the heat flux. So I'm going to give you a quick summary for electron migration and thermal migration. As we mentioned in thermal migration, electron migration part, the driving force actually we use the beta, which is effective charge beta, to modify the driving force. We use, instead of negative chemical potential, electrical potential gradient, we times the beta. Due to we modify the driving force, so the atomic flux change should be modified in the meantime. So the driving force part also have the need to times the beta effective charge. As we remind you before, the sign of the beta also tell you the moving direction of diffusing species. For example, like if the beta is negative, which means that the diffusing species or diffusing positive metal ions moves the same direction with electrons flow. But however, if beta is positive, which means that the species, diffusing species move the same direction as the current. And under this situation, it also implies that there's no electron migration happens. And for the thermal migrations part, in order to easy to remember, so we simplify. We put two terms into we allow two terms into and call them as a heat of transport. So here, as long as you have thermal migrations happen in your systems, you need to times the heat of transport to modify your driving force. And in the meantime, the atomic flow need to be modified as well. And also, the sign of heat of transport is quite important because it tells you the moving directions of that diffusing species. For example, like if heat of transport is positive, which means that the diffusing species move or diffusing atoms move from high temperature toward to low temperature. However, if it's negative, which means that it moves from low temperature against the temperature gradient to high temperature. Okay. Then before then next we just introduce a spatial classes of material we call the vacancy-mediated materials. And we also try to apply a temperature gradient across on these materials and what happens. And are there any additional vacancy or atomic flow we need to consider in addition to thermal migration? So let's give you a quick review. What is the vacancy-mediated mechanism? Which means that the atoms diffuse through this material just by changing the location with surrounding vacancy. This is what we call a vacancy mechanism. So that will be important when if this material inside this material we do have a loss of vacancy, then they will speed up the diffusivity of the host atom. But so based on these ideas, so the concentration of vacancy will be related with the vacancy formation energy and also the environment temperature. So if you do have higher temperature, which will generate the higher concentration vacancy. But if you have a temperature gradient or temperature variations across your materials, then the concentration vacancy will be different. Then that probably will lead a vacancy flux and finally lead the atomic flux with the upside direction with the JV. So what this means, so back to the prior, this case. For vacancy-mediated materials, when you acting the thermal temperature gradient on it, for example, like we have a higher temperature on your left-handed side, but lower temperature on your right-handed side. And in the beginning, probably you will think about thermal migration. So you can easily write down the atomic flux for this material be mobility, concentration, and also the driving force, which is the heat of transport times the negative temperature gradient divided by T. This is what we learned in thermal migration. But however, in this material system, when you acting the temperature variation across these materials, you need to consider additional effect we call the vacancy variation. What this means that In addition to Tm, you need to consider the vacancy concentration variation. It's caused by the temperature gradient you apply on this. So we have a more vacancy on your left-handed side and less vacancy on your right-handed side. So you do have a vacancy variation across this material. So that will lead the vacancy flux to where? To right-handed side, because we have more vacancy on your left-handed side. This vacancy will move to right-handed side. But you have a vacancy move right-handed side, which also tell you that the atomic flow or atomic flux be generate move to left-handed side, which is upside direction with the JV induced by temperature gradient. So we do have this atomic flux due to the vacancy, the concentration vacancy is a difference. Okay, so next, this is just due to the also atomic flux will move to left-handed side, which is go to your left-handed side. But under this situation, we just discussed the first effect, which is due to the we do have a vacancy, the different vacancy concentration induced by different temperature. But if you added the second factor you learned in prior slides is the heat of transport for these metals. Before we talk this, I just give you the results, proof by this paper published in 1964. They say that if you deal with vacancy-mediated thermal migration case, the vacancy formation energy can be put here to modify the flux, atomic flux driven by Tm. In order to prove that this idea is like roughly is good, is correct, so I give you two examples. The second part, thermal migration, you need to define whether this heat of transport is positive or negative. So the first possibility is if we have heat of transport of this material is negative, which means that atomic flux will be moved to left-handed side, move the atoms will move from low temperature region toward to high temperature region, which will be the same direction with this one, induced by different vacancy concentration. So this red flux plus this green flux, you will get the larger atomic flux, final atomic flux, larger one move to your left-handed side. And it makes sense, right? If the heat of transport is negative, you have a negative term minus a positive term. The atomic flux Ji will be get larger. The same with what you perform. The second possibility is to these materials, the heat of transport to this material is positive. Positive means that the atomic flux driven by Tm will be the atom will move from high temperature toward to low temperature. So will be go to right-handed side. And this atomic flux driven by Tm have a opposite direction with the atomic flux driven by different vacancy concentration. So I use this yellow one to minus the red one. So the final, I sum them together. So the final atomic flux driven by both this effect will be move to right-handed side. So let's take a look here. If the heat of transport is positive, you minus a positive term. For vacancy formation energy, in most of cases, is around 1 eV. So usually heat of transport will be larger than that. So finally, I will get after some these two factors together, the atomic flux, final atomic flux driven by both the Tm and also vacancy, different vacancy part, will be moved to right-handed side. We have a smaller than this one because you need to minus the red this red one, which is contributed by different vacancy concentration. Okay, so this results after like I show you. Just want to remind you for when you deal with the metals, spatial class of metal which are vacancy mediated diffusion ones, you not only consider the atomic flux driven by Tm, you also need to consider the atomic flux due to we do have a different vacancy concentration. Okay, you need to sum them together, then you know the final atomic flux driven by both these factors.